Okay, let's go ahead and get started. Welcome to the first class of EE 310 in spring quarter. My name is Craig Barrett, and I'm organizing this seminar class. We have some really great speakers lined up this quarter, as you see from the schedule. There's also a possibility of doing one extra talk. It's possible that we have somebody from Apple who's going to give a talk, which is highly unusual. So that's very exciting, and we'll send out an announcement for that. It's probably going to be in the middle of May. So this class is a seminar. It's basically pass or no credit. So there are no exams, there are no formal quizzes, there's no homework. So it's really only by attendance that you get credit for passing the class. So the way the scoring works is extremely simple. If you attend the class in person, please sign the sign-up sheet if you're registered. If you're not registered, you don't need to do anything. You're welcome to audit the class or just drop in without being registered. If you are doing it for credit, please sign the sign-up sheet if you're here in person. That scores 2 points per seminar. If you can't attend in person, you're more than welcome to attend by Zoom. There's a link that gets sent out so you can attend live. And the Zoom recording will get posted to the SystemX website each week, usually by tomorrow, by Friday each week. So you can also view the recording time delayed at your discretion. In that case, you don't get credit for showing up in class. So I do send out a very simple quiz each week that you have 2 weeks to respond to. It's completely optional. I just ask 2 questions about the material. And if you're viewing remotely or delayed in time, you can use that quiz to score an additional 2 points per seminar. So potentially you can score 4 points per seminar by doing the quiz and attending, and just attend 4 classes to pass. I hope you attend all of the classes, but obviously it's up to you. So that's how the scoring works. It takes a total of 14 points to pass. For SCPD students who do not attend in person typically, although you're welcome to, you only need 8 points to pass because you only have remote attendance credit, 2 points per class. So that's the setup. Please send me an email, or Kia, who is the TA, if you have any questions. We'll be happy to answer them, and hopefully you'll really enjoy the speakers we have. So today it gives me great pleasure to introduce Onur Mutlu, who is a professor from ETH Zurich. He's visiting as a visiting professor at Stanford this year, and he actually gave a talk in E310 winter quarter, which was really great. That's on a different topic, so this is now the sequel, a talk on in-memory compute. And Onur is one of the leading computer architects, and his group does some really interesting research. He did his master's and PhD at UT Austin after doing an undergrad degree at University of Michigan. And he was a professor at CMU, I think, for a number of years. And he's actually still a professor at CMU as well as ETH. He's a busy guy. He worked at Microsoft for a number of years. He actually started the computer architecture lab at Microsoft while he, computer architecture research group at Microsoft while he was there. And he's also worked at Intel, AMD, VMware, and Google, to name drop some leading tech firms. So with that, it gives me great pleasure to introduce Onur, and we look forward to hearing about in-memory compute.
Okay,
thank you.
Thank you very much, Craig. Thank you for the introduction. Thanks everyone for coming. I understand this is your first class of the quarter. I assume no one here has attended my lecture last quarter.
There are some students who are doing it.
Oh, there are some students who are doing it again. How many people are here? Well, certainly Craig, maybe. Okay, I see at least 2. Maybe there's some online. I don't know. It's hard to keep track online. So this was the title of my lecture last time. We're going to continue along this direction. We're going to talk about future computing platform challenges and opportunities. But today we're going to focus on memory-centric computing, in-memory computing. This was what I started covering in the last semester, essentially. Basically, we talked about fundamentally robust, secure, reliable, and safe architecture. So robustness is a big problem going into the future. If you're interested in that, probably you can watch the lecture online. Today, we're going to focus on more fundamentally energy efficient and high performance systems. And I believe that those require us to be much more memory-centric and data-centric. And I'll give you the background and why I think this way. But before we start, I think today it's very clear that computing systems we design today are bottlenecked by data. And data is really key for many, many applications. Important workloads are all data intensive. They require rapid and efficient processing of large amounts of data, and data is increasing. We can generate more data than we can process. We're seeing this in the machine learning domain. We're seeing this in the video domain. We're seeing this in genomics. For example, I mentioned that in the last lecture. I'm not going to talk a lot about genomics today, although I will mention applications of in-memory computing to the genomics domain a little bit. And we want to perform more sophisticated analyses on more data. So this trend is not going to change. Things are going to get complicated. The quick question that we're targeting, that we're asking in this lecture is, are we really designing our systems to deal with data properly, efficiently, and at high performance? And the answer at this point is no, basically. But we'll see how we could basically design our systems in a much better way. So this is just to give you one example from the machine learning domain. This is actually a talk that was delivered by the Cerebras CTO, Shanley. You can find the talk online. These guys are building chips that are this big, wafer scale chips. This is fascinating. Why? Because they want to put a lot of memory and a lot of computation on the same chip so that they can more efficiently process the data as opposed to going back and forth between memory and the processor. And the reason they're doing that is because the computation requirements of models are growing, as you can see over here, and memory requirements are also growing. They're both growing exponentially, as you can see. And you can see that number. We need 1,800x more computation in just 2 years. And this is not going to change for a while, although we should be investigating also much more efficient algorithms. So I'm not ruling that out yet. But this is just an example. There are many, many other applications like genomics that also increase in data. So last time in the lecture, I also talked about Abraham Maslow. If you don't know this person, this is a very famous American psychologist. He's probably more famous than this for this pyramid as opposed to his face over here. But basically, this pyramid is used in many domains. It basically says that human beings need their basic, very basic needs, physiological and safety needs satisfied before they can think about something more important. And I use this to motivate that we need to start building really fundamentally robust systems, safe, reliable, and secure systems, so that we can actually do something much more intelligent with our computers. If we actually are threatened in robustness, we will not be able to trust the machines that we built, like self-driving cars, or if we go to space, for example. So today I'm going to kind of deconstruct that and basically revisit it and say, none of that matters if you don't have enough energy. Who cares, right? If you cannot move, who cares if you're safe? So that's why I think energy is maybe more fundamental. And we're going to talk a lot about energy, even though we're going to talk a lot about performance too. Okay, another picture just to motivate at a very high level. I think going forward, we should really think about what kind of a world do we want to live in? Do we want to live in a world that looks beautiful like this? Hopefully you find this beautiful. Or do you want to live in a world that looks like this? I would probably pick the first one. But I don't want I want also the productivity of the second one, perhaps. Basically, we're greedy. We want high performance, energy efficiency, and sustainability all at the same time. So the question is, are we doing the right things in the design of our systems to achieve these? Okay, so I will give you the problem right away. Today, we're having a problem with data access. Data sits far away from the computation units, and this is the major bottleneck. And the way we're designing our computing systems today require us to move the data between the memory and storage to the processor many, many times. And this wastes a lot of energy, and this wastes a lot of performance. Okay? So for performance, we try to do a lot of things, actually. This leads to moving the data between the processor and memory actually leads to a lot of performance issues like latency, bandwidth, etc. issues. But we try hard to tolerate that. What do? We build extremely sophisticated processors that can execute instructions out of order, for example, to tolerate those latencies. We build huge memory hierarchies. I will show you some pictures soon, so that we can tolerate this. We build massively multi-threaded systems so that we can tolerate the latency that happens in one thread, potentially. And we build prefetching mechanisms, etc., data migration mechanisms. Unfortunately, all of these actually complicate the system, make it more and more complex. And this complexity eventually hits us in energy again. Because this complexity, when it works somewhat, or when it doesn't work, this complexity actually wastes a lot of energy. The memory hierarchy wastes a lot of energy if it's not improving your performance, especially. Okay, so we're in this vicious cycle today. We're trying to tolerate the downsides, performance downsides of data movement by adding more complexity to our systems. And data movement itself actually leads to energy waste. So we're in this vicious cycle of energy waste in our systems. So how do we get rid of this vicious cycle? I think all vicious cycles can be solved by identifying the real problem. And I think the real problem in this case, we're processing data far away from where the data is generated or stored. And this talk is all about this, basically. Okay, feel free to ask questions, by the way. You can interrupt me. No, I don't have a problem. If there are questions on Zoom, that's also okay. So basically, today's computing systems are overwhelmingly processor-centric. All data is processed in the processor at great system cost. If you look at any computing device, you have, oh, sorry, somehow I clicked the wrong button. You need to have a computing unit, a communication unit, and memory and storage unit. We've decoupled our systems significantly, and we made our systems such that the computing unit is the only place that can do some operations on the data. Everything else over here cannot do any operation on the data in general. As a result, we move data between the computing units and the communication units and the memory and storage units. Okay, so this is my actually cartoonish picture. I drew this picture in 2008 when I wrote my first NSF, National Science Foundation proposal. Not a whole lot has changed, although things are changing, as I will tell you. So if you look at this picture depicts a modern multi-core processor or a heterogeneous processor with many accelerators. Cores can be accelerators also. If you look at this picture, cores are a small part of the component, small part of the resources. Everything else is there to move or store data. Caches, interconnects, other interconnects, memory controllers, other interconnects, memory, other interconnects, storage. And if you do the calculations, more than 95% of the hardware real estate of a single node is dedicated to storing and moving data, not computation. Of course, if you tell this to someone and say, you don't expect data movement would be a problem here, right? Because you're dedicating almost all of your resources to that, to storing and moving data. Well, unfortunately, that's not the case. The entire system is still bottlenecked by memory and data movement. So maybe we're doing something wrong. Okay, if you don't like my picture, sorry. If you don't like my picture, this is AMD's picture. It's a real chip. And this box over here, this green box shows the L2 and L3 caches. That's most of the chip. Now, wait, the global memory interconnect is up there, and then a bunch of other memory is over here. So most of the chip, not a node, just the chip itself, is really dedicated to memory and data movement, memory and interconnects, sorry. And we're adding more. This is beautiful technology, 3D stacking technology. It's used to add more caches. So this is the memory hierarchy that we're building. If you don't like AMD, this is IBM. Basically, the same thing remains over there. I could keep going on and on, but I'm going to stop here. Maybe I will mention this one since Craig mentioned Apple earlier. This is a beautiful SoC over here. I would consider this compute chip as a lot of SRAM, mostly. And then there's this darkness, which is DRAM. And then there's the real darkness, which is usually forgotten when we build systems, storage. So maybe we should really be thinking about doing computation in all of these places. Okay, so data today overwhelms modern machines, actually. It overwhelms our storage capability, communication capability, and computation capability. And we're actually building very, very sophisticated computing devices, yet they're being starved because they cannot get enough data to compute on. And I'm going to give you numbers. I'm going to motivate all of these with numbers. It also greatly impacts robustness, energy, performance, and cost. We talked about robustness in the previous lecture. If you're interested in robustness, I would definitely, and security and safety, I would definitely recommend watching the lecture from last semester. So what is the impact of data or memory on the system? We've known that this is actually a big problem. So this is Dick Seitz. How many people know about Dick Seitz? Older people probably do. Dick Seitz was the chief architect of the Alpha architecture. How many people know about the Alpha architecture? Okay, good. Alpha architecture doesn't commercially exist today, but it's one of the nice RISC architectures that used to compete very well with the highest performance processors. It was actually the highest performance processors of its time. And Dick Seitz group designed one of the highest performance chips. After they designed one of the highest performance chips, he wrote this paper. It's a one-page paper. I'd recommend reading it. It says it's the memory stupid. It's all about the memory, basically. He basically says that we designed this processor to complete 4 instructions, four alpha instructions every clock cycle. Unfortunately, in this important workload, it's finishing 1 instruction every 4.7 clock cycles, meaning it's operating at less than 5% of its peak bandwidth, peak computational throughput. Why? Because it's waiting for data to come back from memory, even though it has a sophisticated cache hierarchy. And he finishes this article by saying, I expect that over the coming decade, memory system design will be the only important design issue for microprocessors. It's a beautiful paper. I recommend reading it. Okay, that's Dick Seitz. This is data from my own research, from my PhD thesis, actually. My first paper that was published at HPCA in 2003. We studied many applications, hundreds of applications from Intel's suite at the time, at a high performance processor. And we found that essentially the same thing. Most of the time, the processor is waiting for data, even though it has a lot of computational capability. Okay, if you're interested, you can read the paper also. Okay, if you don't believe Dick Seitz, if you don't believe me, since everyone believes Google, this is data from Google, as you can see. They published this beautiful paper in ISCA 2015, where they showed that, according to them, in all of their data center workloads, a state-of-the-art processor waits for data most of the time. Basically, it's spending its time waiting for data. That's the red parts over here. It's finishing instructions only in the green fraction, which is less than 10 to 20% of its time. Well, it's waiting for data, basically, even though it has a sophisticated memory hierarchy that I showed you earlier. Okay, so this was performance. I motivated data access a major bottleneck. I think this is well known, and now you have some data. I'm going to give you more data later on. Energy consumption is clearly a key limiter today in many systems we design. I'm going to take that as granted. I'm going to talk about now this third issue, which I think is even worse than performance, which is the energy, data moment energy dominating computation energy. And I'm going to use someone else's data. This is Bill Daly, who was the chief scientist of NVIDIA, who was a professor over here for many years. He basically has a slide, which is relatively old, but it gives the idea. Essentially, here we're comparing the energy cost of different operations. And this operation over there, a 64-bit double precision floating point operation, consumes only 20 picojoules in this technology. And memory access is 16 nanojoules. That's 800x difference. Now, if a memory access consumes 800x the energy of a very sophisticated operation, does it really make sense to actually bring the data, multiple pieces of the data, by paying that 800x to do a relatively cheap energy-wise operation and then write the data back? Now, of course, this is a mathematical equation, right? Where scientists and engineers, you can optimize things, and you can figure out when you would actually amortize that cost. You could amortize that cost assuming you have locality in the data. You keep reusing the data without going to the memory. To be able to do that, you need to reuse that data thousands of times. You can actually do this calculation yourself if you're interested. And many workloads don't have that kind of locality. Imagine a random access workload that doesn't have any locality. Of course, this is an extreme, but those kind of workloads actually exist in some domains. In that case, you're actually bringing data to the processor and never reusing it. So that cache hierarchy is essentially useless. Okay, maybe 800x is too much. The real number today is between 100 to 200, I would say, if you optimize it. But 100 is still pretty high, right? Okay, but that's not the full story. This was a sophisticated double precision floating point arithmetic operation. Now, if you go to a simple integer add, 32 bits, that disparity goes to 6400x. Okay? Now, this 32-bit add, what are we doing in machine learning today? We're trying to get rid of the precision, right? Why? Because we actually can do with less precision, and energy is a big issue. So if you go to a 4-bit add, that number actually amplifies significantly. And this is just memory, accessing memory. Think about storage. Storage even farther, add 10x more over there. So if you're actually moving data from storage to memory, memory to processor, you're consuming a whole lot of energy to do a very simple operation in terms of energy. Okay, so hopefully I made my point clear. So we did a lot of work with Google. In my prior sabbatical, I spent some time at Google. And we found out that on important mobile workloads, a general set of workloads, more than 60% of the total system energy is spent on data movement. I'm going to talk about this paper later on if we have time. And this is an average use case. If you actually go to more data-intensive workloads, that number shoots up to 90%, 95%. Later, we actually repeated the study with Google on edge machine learning systems. You have a machine learning inference system running on HTPU, tensor processing unit, specialized accelerator, basically. And we found out that more than 90% of the total system energy is spent on memory in those kind of workloads, especially the large machine learning models, which we're building today. And if you look at actually larger and larger models, this number goes up to 99%, 99.9%. So I think we do not want to move data, basically, going forward. We need to design our systems such that we process the data without much movement. And that's the idea of memory-centric computing. This clearly requires a paradigm shift because we've been designing our systems to be processor-centric for many, many decades. We would like to enable computation with minimal data movement. We would like to compute where it makes sense, where data resides. If it makes sense to process in the processor, fine, process in the processor, right? If it makes sense to process in the sensor, process in the sensor. If it makes sense to process in the storage, process in the storage. And this is the idea of data-centric computing in general. Essentially, we have many places to process the data. Why are we restricting ourselves to a particular place within this chip, right? Even this chip can process data in many places, like L2 caches, L3 caches, but we're not doing that today. Okay. Okay, now let me give you, we're going to talk about some techniques. The high-level idea, I'm going to focus on memory and storage. but the general idea of data-centric computing applies to processing inside the sensors network while the data is moving, etc. So there's actually a whole world out there, I would say. I'm going to focus on memory, especially. I'll talk about storage also. These things are relatively similar. And especially, I'm going to talk about DRAM, which is essentially all of the main memory that we have today. In my pocket, I have a cell phone. It has a lot of DRAM. And it's consuming a lot of energy right now, actually, by refreshing itself, for example. That's the main memory. OK, so what we would like to do is we'd like to store applications in the memory device. And we would like the processor to ask memory device to execute operations on the applications, on the data, essentially. So we can query the data, for example. And the memory and storage does the computation and returns the results. Now, there are many questions over here. Basically, how do you design the compute-capable memory and the controllers? How do you design the processors and the communication units? Basically, what goes on inside over here that I didn't show. I'm going to talk about that. How do you design the software and hardware interfaces to enable that? How do you program this? How do you design the system software compilers and languages to make it easier to enable this sort of system? Because none of these are able to do this sort of computation today, although there's a lot of research, as you will see. And how do we rethink our algorithms to actually match the computation capability in memory? If you think about it, today algorithms are designed completely for processor-centric systems. And also theoretical foundations, I will mention that. So this is an exciting across-the-stack realm. You can design devices that can do computation inside memory. You can design algorithms to match that. And you can actually design the entire stack to enable it. And that's what's really exciting about this area. One thing, maybe I'll ask, how many people have taken a theory of computing course here, computational complexity course? OK, how did you quantify the computational complexity of algorithms? Big O notation. I'll answer it quickly. Basically, you count operations, right? Now, I've shown you a lot of data to say that maybe operations don't matter, right? Maybe what matters is the data moment. So even the theory of computing is highly biased toward processor-centric systems. We don't have a data-centric theory of computing, essentially. So we really need to reinvent computing, I would say, to do truly memory-centric computing. OK, so I should also say that this is not a new idea. At least part of it is not a new idea. A lot of smart people in the 1960s, at least, thought about it. This is a beautiful paper. They called it logic in memory. This is a form of near memory processing. Basically, they're adding logic closer to memory. Actually, some folks, Harold Stone, who used to be at the Stanford Research Institute, wrote this paper that also talks about something similar. Now, what's different? I will mention quickly. I think today the landscape is very different. At the time, and people have examined this idea many, many times over many decades. Today, we're actually kind of squeezed. Today, we're having a lot of problems with memory technology. It's not going well. So we actually need intelligence in the memory controllers to overcome the technology scaling issues. I'm not going to talk about that. We actually talked about that in the previous lecture, robustness lecture. If you want to learn about that, go back to the robustness lecture. So technology is pushing us to be more intelligent than the memory controllers. And as I said, applications are also pushing us to do something different. We want performance, energy, and sustainability at the same time. And we want to improve all metrics. And if you actually do data-centric computing, we can improve those. So we're kind of squeezed in the middle. That's why I think data-centric computing is kind of happening today. So if I was giving this lecture 5 years ago, you wouldn't be able to see any of the chips over here. So industry is actually picking up. So people have today 3D stacking, 3D stacking systems where you have memory stacked underneath or on top of logic. And you can actually add computation over here. We're going to talk about that. This is hybrid memory cube or high bandwidth memory. People are experimenting with chips that can, DRAM chips that can do computation. More recently, the UpMem company, this is a startup in France, introduced DRAM chips that can actually do general purpose computation. You can actually buy this. You can actually program it. We have tutorials where you can actually get hands-on. It's fascinating, I think, even though it has idiosyncrasies. And more recently, companies like Samsung, SK Hynix, more Samsung, and Alibaba have introduced DRAM chips that can actually accelerate machine learning applications by supporting matrix vector multiplication, for example. These are also fascinating chips. You cannot necessarily buy them yet, but they have prototypes internally, which other people have used. So, and there are many other experimental chips and startups. Is there a question? OK. I thought there was a hand, but. With interfaces like Compute Express Link, which is an industry standard today, you could actually decouple processor and memory, and you can offload computation to the memory side. That's why you actually see other prototypes. Here, SK Hynix has an FPGA next to the memory, for example. and you can do processing in that FPGA that's next to the memory. Samsung has something similar also. Again, I'm not going to bore you with these right now, but if you want to learn more about this, we have a large, long paper that talks about a lot of issues related to processing in memory. I will cover some things inside this paper right now. And we also have a processing in memory course if people are interested in attending. A lot of our courses are online, and you can find them. And we have tutorials that you can find. Okay, any questions so far? Otherwise, I'm going to jump into some techniques to enable these things. Okay, let's jump into techniques. So I would argue that we need to think differently from the past approaches. We need to actually think about how we do comprehensive processing in memory and how we enable it to the end user, like the programmer. I will now define two types of processing in memory. I think there are two fundamentally different types in terms of nature of processing. And I'm going to pick processing using memory first. Let's see if we can finish this one. I believe we'll finish this one. I don't know how far we will get in this one. So let's start with processing near memory. What does this mean? So you have a processor, logic, and you have memory, a memory device. Processing near memory says, put the logic closer, 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 and at some point integrate it in the memory device. It could be inside the memory device. It could be near the subarray, inside the subarray, in a 3D stacked logic layer, etc. But logic and memory are separate. You design logic as logic, memory as memory, and combine them. Logic can become near the memory. If it gets near, that means that you don't have the overheads of the interconnects. Okay, so this is more conventional, I would say, and this is why all of the prototypes that I showed you over here, well, I showed you somewhere over here, are processing near memory prototypes. Processing using memory is something very unconventional, and this is what people have envisioned in the 1960s. Processing using memory is more recent, and the idea here is you have logic, you have processor. Normally, you design logic to do computation, right? Forget about logic. We have memory. Normally, you design memory to do storage. But no, this memory can do storage, but also do computation. So can I actually see this memory device as a computational device also and exploit its analog operational properties to do computation? And that's the idea over here. And I found this fascinating. This is a lot harder to do because it's more analog computation. But we need to enable this because I think this is fundamentally a much more energy efficient form of computation. That's why I'm going to start with this one, even though it's longer term. In the end, I believe we really need a combination of both. We really need processing capability everywhere, both analog and digital. Okay, so I'm going to skip this taxonomy, but maybe I will just say that this was just the nature. There's also different technologies that can do computation. I'm going to talk about some of them. There's also different locations where you can do computation. And so you can actually define a tuple of these three as a PIM type, and I believe you need to explore all of them. Okay, so mindset going forward, what I'm going to describe is going to be as an accelerator. Because if you actually take what I said to the extreme, everything should be able to do computation independently. Everything should be an independent agent, meaning there should be no special status to the processor. Everything is a processor. In the end, you have distributed agents, and these distributed agents communicate with each other to get a task done. I think that's a great direction going forward, but I think that's an even larger step to take. So the step we're going to try to take is to see memory as an accelerator. The processor is still the central processing unit, if you will, but we will accelerate the tasks by offloading things to the memory side and different parts of the system. Okay? And we know how to design accelerators. Clearly, we've been designing a lot of accelerators, except they're sitting on the left side of the memory bus, and not the right side of the memory bus. No pun intended. Okay, so basically we're treating memory as a conventional accelerator, and then that means that the programming methods are going to be somewhat similar to the conventional accelerators, although there will be challenges, as we will see. I'm going to focus on processing using DRAM in main memory. So basically, let me give you the takeaways. This is based on some of our research, as well as some of the other research that built on our research. We can support a lot of operations in DRAM, bulk bitwise and or not majority, without significant modifications to the DRAM circuitry. We can do bulk bitwise copying and initialization. We can do true random number generation, physical unclonable functions in real DRAM chips today, actually, without modifying them. And we can do lookup table-based, more complex computation as well, at low cost and using analog computation capability of DRAM. I'm going to give you the ideas a little bit later. And you can get significant performance energy improvements. These are some initial papers that talk about this, but I'm going to give you some more papers. Now, let me start simple to talk about, like, what is the simplest thing that you can do without significant modification to DRAM? That's always a good approach. How can I actually do the simplest thing to get some benefit out of this memory device? And I'm going to cheat. I'm not going to talk about computation. I'm going to talk about data copy and initialization, which is really important, actually. There are many applications, like imagine starting a database that's 10 terabytes. You really need to initialize that 10 terabytes, right, physically. And that's a lot of energy. But there are many applications that do data copy and initialization. In fact, in that paper that I mentioned from Google, they showed that in these two function calls, system calls, memmove and memcopy, essentially occupy 5% of the cycles, execution cycles in the Google's entire data center. That's fascinating to me. Only two function calls, right? Okay, how do we do copying today? If you want to copy, let's say, a 4 kilobyte page, the white page to the gray page in memory, you go through the processor, because there's no one else who can do this. At least the memory controller, if you know about direct memory access, that's part of the processor also today. So basically, you copy the source page, the white page, byte by byte into the caches, and the destination page, and then do the copy and write back the destination page byte by byte to memory again. This is high latency, clearly, high bandwidth utilization on the memory bus. You cause cache pollution, and you cause a lot of unwanted data moment, because you may be doing a lot of this copying without reusing any part of the page also, right? So in a modern system, for a small copy, 4 kilobyte page copy, going through just the memory controller without disturbing the caches, it takes about 1,000 nanoseconds and 3.6 microjoules. I'm going to give you a mechanism that actually reduces that significantly. Now, if you show that picture to a 10-year-old child and said, how do I do this copy? Maybe they would come up with, oh, why don't you just go through memory, right? They're just both sitting there. And that's the idea, basically, in-memory copy. The question is, how do we actually support it? And it's going to be relatively easy. So the benefits are, this is low latency. This is low bandwidth. You don't actually waste bandwidth on the memory bus. No cache pollution, and no unwanted data movement. So the mechanism that I'm going to describe will take that 4 kilobyte copy from 1,000 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules. Now, you can optimize this further also. And the idea is to do this in DRAM. This is the best case of the mechanism, of course. But I'm not going to talk about the general case, which you can think about or read the papers. So let's go a little bit deeper. This is a DRAM subarray, meaning that it's a two-dimensional array of cells. Each cell stores 1 bit of data. And a row is 4 kilobytes in this particular case. And you have sense amplifiers that store a row that you activate. So if you want to read something in one row, you first activate one row, which stores the data, which gets stored in this row buffer in sense amplifiers. And sense amplifiers are much stronger than the cells. Now, the idea is to first activate the source row, which brings the data into the sense amplifiers, row buffer, and then activate the destination row while deactivating the source row. Activating the destination row connects the sense amplifiers to the destination row, which means that you take the data that was written into the row buffer and store it into the destination row. By doing these two consecutive back-to-back activates, you use the row buffer as a temporary storage of the source row's data and then write it to the destination row. This is negligible hardware cost, almost no hardware cost. In fact, you could do this in existing DRAM chips by violating the timing parameters. Existing DRAM chips do not support this officially, but if you violate the timing parameters such that activate to activate timing parameter is violated, you can get this behavior quite reliably. I will mention that also. So what is the benefit? You reduce latency by about 11x, and you reduce energy, DRAM energy, by about 74x. Now, of course, we want to be more general. You want to move data between subarrays and between different banks in DRAM. I'm not going to talk about that. Initially, when we did these studies, these numbers were much higher, but you could actually add more support for this data moment in DRAM. And this is the idea of row clone. Now, later, people who actually read our work and used some of our infrastructure to do DRAM testing showed that by violating the timing parameters, you can mimic row clone and do this reliably in existing chips, off-the-shelf chips. And we built on their work nicely to release an FPGA-based processing in DRAM system. You could actually use this yourself if you're interested in FPGAs, for example. The idea is we can run end-to-end applications over here. Of course, there are some limitations. But if an application does memcopy, that memcopy gets shipped from the RISC-V processor that's running that memcopy to the memory controller, which is on the FPGA. And the memory controller violates the timing parameters to do the memcopy inside the DRAM. And this works quite reliably. And this way, you can actually test end-to-end performance benefits. Okay. I don't want to leave the meeting, I think. Yeah, this gets significant end-to-end system benefits. And you can read the paper for more detail. If you're actually interested in doing hands-on studies, we'd be happy to support it. It's a lot of fun to do this. This also supports true random number generation, which I'm going to briefly talk about. Okay, there are many extensions to this that I'm not going to talk about. Basically, can you move data from here to there, etc., with a little bit more cost? Yes, you can. And these are the papers if you're interested. Okay, now that was not computation, right? This is data copy. Initialization is a special case of data copy, right? If you want to initialize a row to zeros, you write zeros to one row, and then you copy that row everywhere you want to have zeros in. I'm going to now talk about computation, unless there are questions. Okay. Okay, I already said all of this. How do we do computation? Before I say that, I should say that I'm going to focus a lot on DRAM, but other memory technologies enable even more opportunities. Some of these technologies can do matrix vector multiplication in the analog domain, and that's actually useful. In DRAM, it's very tough to do matrix vector multiplication. So what can you do in DRAM, which is the really dominant memory technology that you have today? I'm showing you here three DRAM cells, 3 rows. Only 1 cell per row in this case, but imagine that you could do this same thing in 8 kilobyte of data or 4 kilobyte of data. And you could potentially do this on thousands of different subarrays, meaning you could actually do operations on 8 million, 10 million bits at a time. So what is the operation? The idea, the primitive, is triple row activation. If you activate these 3 rows concurrently in DRAM, what you get is a bitwise majority function. So these are cells that are charged. This is a cell that is not charged. These are capacitors, essentially. If you connect all 3 of these capacitors to the same bit line, they perturb the bit line. And assuming an ideal circuit, if at least 2 of these capacitors are charged, you get the charge state at the end. If at least 2 of these capacitors are discharged, you get the discharge state at the end. Now, what is that? That's a bitwise majority function, right? Well, that's bitwise majority. That's a Boolean equation. This is actually computation, basically. By doing triple row activation, you're doing computation on rows A, B, C concurrently on 8 kilobits in a bitwise manner. Now, bitwise majority is beautiful. Donald Knuth, actually, in his beautiful sequence of books, he talks about bitwise majority or majority function in general. If you take out C, if C is 1, you get the OR of A and B. If C is 0, you get the AND of A and B. Now that's AND and OR. Now we're missing something. This is beautiful, but it's not functionally complete. If you want functional completeness, you need a NAND or NOT on top of this, right? But NOT already exists, actually. If you activate row A, you get the value of that capacitor over here and the complement over here, because this is a SEMS amplifier, essentially. It's essentially a SRAM cell, cross-coupled inverter. I'm not going to talk about that exactly, but that exists. You just need to supply it to the right place in the array or in some other array. So this incurs a little bit cost, but we actually have the inversion or complement function or NOT function also. So this is essentially a functionally complete general purpose substrate with some modifications to DRAM. But this is bulk bitwise. You're actually doing bitwise operations on 8 kilobits of data, and you can actually do this on many, many subarrays. So what is it good for? Well, it's good for everything, meaning you need to rethink your algorithm to take advantage of this substrate. But the good news is there are some algorithms that are actually already designed to operate on large bit vectors. For example, bitmap indices and databases. People actually design databases to operate on large bitmaps. Bit weaving, for example. People have designed web search engines to operate on large bitmaps. You could think about it. Bloom filters, for example, operate on large bit vectors. There are many algorithms that actually fit this nicely. So what we did was actually took some database algorithms and also set operations, etc., and ported this to our simulator that can simulate the behavior of the system. And we see significant performance energy improvements. This is an example from a particular query. You see 4 to 12x performance improvement. And as you increase the size of the data set, performance improvements also increase, which is something that you really want actually in your system. Okay, I'm not going to bore you with a lot of data, etc. You can read the papers, but I just want to give you the basic ideas of these operations. And these are the papers that talk about this in more detail. Any questions? Yes, please.
The signal to noise.
Yeah.
So from the signal to noise point of view, you have 8,000 of these capacitors.
Yes.
Can you will the output be reliable? Can you trust that you always give the correct result?
Yeah. So it's not the number of capacitors, but it's the variation across the capacitors that actually lead to a problem. Right. So number of capacitors, because all of them operate independently. There's another copy of this over here, another copy over here. They operate independently. But if there's a lot of variation in the size of the capacitors, then you may not get the bitwise majority function. And that's a very good question. You really need to keep variation under control. But that is the general challenge with this sort of analog computation, circuit variation and noise. And that's something I think we need to investigate a lot more. And that ties into the robustness lecture that I have. Very good question. Okay. There are later works that actually look at that issue, like variation and also error correction mechanisms. How do you actually correct some of the errors that come up? If you're interested, we can talk more. Okay. So one of the directions that I'm going to describe is how do you program this? How do you make this a general purpose substrate? And this is the idea of the SIMDRAM. It's a framework. I'll give you the basic idea. Essentially, you can implement any operation this way. The user needs to think about the operation. It could be convolution. It could be matrix vector multiplication. It could be a simple addition. They need to express it in hardware logic that looks like this, essentially and or not logic. We convert it to majority inverter graphs. And then we use design automation techniques, essentially compilers, to minimize this graph and convert it to DRAM commands, which is row clone operations and ambit operations and other activates and precharges. So these can be all automated. I'm not going to go through the details. You can read the paper, of course. But basically, you can associate a particular operation like a convolution with a microprogram that's stored in memory. And if you want to call this operation in your program itself, you basically insert this instruction, let's say matrix vector multiplication, and that gets shipped to the memory controller, and memory controller executes the microprogram associated with that instruction. And that way you can actually incorporate any type of operation over here, which is interesting. And we show in this paper that by doing this sort of integration, you get significant benefits over CPUs and GPUs across many operations, and also real-world applications as well. Again, numbers are very interesting. Clearly, these are large numbers. But remember that we're actually showing benefits over technologies that have been matured over 40, 50 years. This technology has not been investigated for even more than 5 years or so, I would say. This paper was published in 2021. Yes.
Question. So there seems to be a locality issue. You have to make sure that in a system with a lot of DRAM banks that you basically are operating within a single chip.
Yes.
And
absolutely.
so you'd have some pragma or some directive that would try to get the OS has to cooperate too, because with virtual memory, you can't really guarantee that.
Yeah, absolutely. Basically, you need mechanisms to map the data appropriately, such that the data that you need to operate on is in the same bank.
Yes.
Or you move it with the mechanisms that we did, like the row clone type of mechanisms from bank to bank, etc.
Okay, thank you.
Yes. And that's in general a challenge, and we're trying to automate that right now. So programming frameworks and data mapping frameworks are really important to get the benefits of this. I mean, that's also important in CPU-centric applications also, except there has been like 70 years of research dedicated to locality, right? So are aggregating data into the caches. Yeah. Okay. I will not go into more detail over here, but essentially, recently, this was HPCA conference last month, we introduced another substrate called MIMDRAM. One of the downsides, well, there are multiple downsides, but one of the downsides of the sort of processing that I mentioned is the granularity. You have to operate on 8 kilobytes of data. But what if your applications have smaller granularity operations like 512 or even less? Here, we actually propose a substrate that can do that flexible granularity operation. And we also have a compiler that can actually compile into different granularities, different operations. If you're interested in that, you can look at this paper. And we have source code available also, and we will keep adding the source code online. Now, let me talk about what else you can do. So these are relatively simple bit serial operations, right? Of course, you can build multiplication, etc., like we discussed on top of those. But some operations are actually very expensive. For example, averaging or square root. I'll take that. And these are not easy to implement using these substrates. So we have a substrate that can do lookup table-based computation. If you have taken a logic course, you've probably seen logic using computation using lookup tables, right? Essentially, we can do the same thing in memory. I will not talk about that, but you can read the papers. We also have been very interested in designing a security substrate in DRAM. I'm not going to talk about the Prof example, but I'll talk about this example. Essentially, you can generate random numbers in DRAM. And we do that in real DRAM chips. This paper is based on real DRAM chips. Essentially, we tested many DRAM chips. If you violate the timing parameter to access a DRAM chip, some cells fail at a 50% rate, meaning once you access that cell, it fails. Another time you access it, it doesn't fail. And you can use that as a random number generation signal. Essentially, we call these random number generator cells. If you profile your DRAM and figure out which cells are random number generator cells, you can actually generate random numbers at very low overheads in DRAM. And this is what this paper shows. This is actually fascinating because you don't need to change anything in DRAM today to be able to do that. You just need to change your memory controller. We also show if you activate 4 rows, you get a random number generator also. That's much better than the previous one. And more recent work that we haven't published yet shows that you can actually activate many rows in DRAM, and you can actually get even better DRAM random number generators. Now, why is this interesting? This is interesting because this is very low overhead. And if you're actually doing processing, if you're pushing computation to the memory side, one of the things that we want to push to the memory side is security critical computations, right? And a lot of the security critical computations require random number generation or physical unclonable functions, which I didn't talk about. You really want the substrate on the memory side so that you can do secure computation. And I actually believe system security can be improved significantly by not moving data around. Meaning if you have a security critical function, do it close to where the data is as opposed to moving the data around. Because if you move the data around, you're actually opening up possibilities to side channels and also eavesdroppers that can actually look at your data. Okay, we have more work on true random number generation. So we also published this work recently at HPCA. I will very quickly give you the high-level overheads, high-level overview. Basically, we found out that existing DRAM chips without any modification, ambit required modification, we can actually perform functionally complete Boolean operations like NOT, NAND, and NOR. This is existing DRAM chips. I'm not going to tell you how, so that's the suspense. You can read the paper. It's fascinating to me. And you can actually do many input, more than 2 input and an OR operations. In fact, 16 input and an OR operations by essentially activating many rows. Now, let me, this paper also talks about it. So basically, you can simultaneously activate up to 48 rows in existing DRAM chips by violating the timing parameters. You can do a NOT operation with up to 32 output operands. And you can perform 16 input AND, NAND, OR, and NOR operations. This is real DRAM chips. No modification to the DRAM chip, just the memory controller. We do this using our FPGA-based infrastructure that I didn't show right now, but I showed it in the previous lecture. If you're interested, you can take a look at it. So we do a lot of FPGA-based testing of the DRAM chips to understand that. So these can be quite reliable also. You will see in the paper that the success rate is relatively high, even though the DRAM chip is not designed for this purpose, right? Now, why is this interesting? We're not suggesting that DRAM chips should be abused this way. But this shows that this DRAM chip that people are designing as memory actually has a lot of computation capability, right? This is really evidence that even though people did nothing to enable this computation, the computation capability is already there. Now, imagine what you can do if you actually go and think about this memory chip as a computational chip, right? You can actually do a lot more reliable and interesting computation on top of this. Okay, how much time do we have? I'm also happy to take questions.
Yeah, maybe wrap up in the next 5 minutes.
Okay, 5 minutes. Okay, I'm gonna
Q&A after that. Yeah.
Sure, I'll wrap up. So I will. I went slower than I thought. Maybe it was faster for you, but we don't need to cover everything. I'm happy to come back to talk about near memory computing. So flash, you can do everything as I said in flash memory also. Now, a lot of the fundamentals we developed using DRAM, but the basic ideas are actually applicable to other chips. You can do this in flash memory. I will not tell you how, but you see, well, I will tell you how actually. Essentially, you can activate 32 rows. And if you activate 32 rows concurrently in the DRAM chip, in a flash chip, you get the AND operation, bitwise AND. Very similar to DRAM. This also happens on PCM, as I will mention later. And this is really reliable. We tested a lot of real flash chips, and we made it reliable. So you could actually execute real applications on this flash chip. And again, I'm going to skip these because we don't have a lot of time. Sorry about that. It's a functionally complete operation. So you can actually remap your applications to this sort of system. And again, that's the challenge basically. How do you map your application to this sort of execution substrate? Okay, but we see significant performance energy improvements. Okay, maybe I'll mention this one also very quickly. Essentially, emerging non-volatile memory is also capable of this. It's not our work. Other people have shown that inspired from some of the things that we've discussed. You can actually do multi-row activation in emerging non-volatile memories like phase change memory, STT-MRAM, and you get similar results. And as I said, emerging non-volatile memory technologies are capable to do even more. So DRAM is, I believe, limited to bit serial operations, although People can innovate better, perhaps. But emerging memory technologies have the matrix vector or a three-dimensional structure such that you can actually feed analog inputs to weights that are stored in a two-dimensional array. And you can actually do vector multiplication on the matrix that's stored in the array, which is actually this thing that can accelerate machine learning, as you can see. Okay, maybe I'll cover one thing in near memory, and then we're going to stop.
Sounds great.
So near memory, we don't have a lot of time. Maybe in a future lecture, I'll cover it in detail, but I'll give you a teaser. So near memory is very interesting also, but it's more conventional. But you can still do relatively unconventional things near memory. I'm going to mention one thing relatively quickly. So when we first started doing processing near memory, we wanted to really specialize things for applications, right? So one of the things that we were really interested in, graph analytics. Graph analytics is very interesting because it's very hard to scale to a very large number of nodes. So why? Because you have a lot of random memory accesses, and you have little amount of computation. There is some locality, but not a huge amount of locality. So if you actually don't have a lot of locality, pushing computation near memory actually makes a lot of sense, as we discussed. So we actually built upon these three-dimensional memory technologies. This is high bandwidth memory or hybrid memory cube at the time. You have memory layers on top of the logic layer, and you have high bandwidth, low latency through silicon via connection. So in this logic layer, you can build essentially any logic, and on top of it, you have a lot of memory. That's the idea. Now, what can you design based on this? Unfortunately, you cannot build huge amounts of memory, so you need to have a distributed system. Our idea was to have an accelerator that consists of these three-dimensional cubes. And in the logic layer of each cube, you have a lot of processors. They're interconnected in some way. And if you look at each of these processors, there's a simple in-order core and a memory controller. And what we do is we connect many of these cubes together so that you can actually scale to a very large graph. And you do partitioning of the graph so that you have hopefully some amount of locality. And the idea is whenever you do an update on a graph node, you don't move the data, you move the function to the data that's stored in that node. So every node stores some part of the graph because it's partitioned, and the updates are sent to that particular core using remote procedure calls. So this is remote function call based programming, which is actually used in distributed systems today. The programming method is, but we're doing it on chip, as you can see. And we also have a lot of prefetching mechanisms because there's ample bandwidth that's available to the cores. There's a lot of system design decisions over here. I'm not going to talk about that in detail because we don't have time. But this system looks very different from existing systems at the time. Existing systems have all the memory bottleneck because memory and processor are different from each other. Here, memory and processor are combined with each other, except you have a distributed system of that memory and processor. And at the time, 8 terabytes per second was a very large number to have for these 512 processors to have access to. And we show significant performance improvement. So you can see that on 5 graph processing algorithms, you get more than 13x performance improvement. And the energy reduction is also similar. This was work that was done in 2012, published in 2015. And a lot of work's built on it, actually. And those numbers in more recent works are closer to 100x, both energy and performance. So you can actually improve performance by around 100x and energy by 100x. And if you want to improve energy delay product, you can multiply those two. So you can actually do near data processing is also interesting. Even though it's more conventional, as you can see, it can lead to significant improvements. Okay, and that's the paper if you're interested in looking at it. And I have lots of other papers that I'm not going to talk about, but I'm going to, I think, conclude right now. What do you think?
Perfect.
Should I go to my conclusion slides or take questions? Okay.
Yeah, what conclusion slide would
Maybe
be great.
before the conclusion slide, I should say that adoption is really important. You can build any hardware. In the end, you really need to do everything else in the system, especially programming, to get it adopted. And these are some of the challenges that we're trying to solve right now. Maybe in a future talk, I'll talk about near memory and its adoption. But I believe, most importantly, in order to enable adoption, we really need to change the mindset. So if you think about the way we design computers today, essentially every single design decision that we make that's important assumes there's a central processor. We got to break that if you really want to actually change the paradigm. It's not easy. It will take time, but research is the right place to do it. I think this is where I will probably conclude since we don't have a lot of time. I'm happy to take any questions.
Awesome. Well, thanks for a great talk on it. Thank you so much. Great.
Sure. Thank you.
So we'll post the slides hopefully tomorrow, and you notice many of the slides had links to papers and more information. So all of those links should be live in the posted PDF. So that's the easiest way to follow up. And if you want to dive into any more detail, if you arrived late and you're doing the class for credit, don't forget to sign the sign-up sheet, which is up front here. So let's open the floor for questions. Let's take some questions locally first. So, right.
Hi. So I see that some earlier PIM models like SRAM PIM or processors using memory, they are kind of like small scale in edge scenario. And like you just mentioned that in DRAM, you can only like do 3 rows of activations. And it seems that it's already bottlenecked by the variation and signal to noise margin. Do you think it can make this to a larger scale, like a server scale, supercomputing scale?
Mm-hmm.
Yeah.
I believe the answer is yes, because this is really research at its relative infancy, right? SRAM models also have variation issues, maybe not as much as DRAM, but they're also doing you can actually do all of these operations that I mentioned in SRAM also. So the primitives are actually relatively similar. The technology also determines the reliability, as you mentioned. But I believe all of these can be done in very large scales. That's what we're shooting for, actually, enabling more reliable operation and enabling more programmability. Are we there yet? No, I don't think so. But also keep in mind that these processing using memory ideas have been really starting to get around in 2014-15 timeframe, as opposed to more near memory processing ideas that were around since 1960s.
The next question.
Yeah, and so for these within DRAM computations, for example, the majority function that you described, do you end up wiping the data that you're computing on?
Absolutely, yes. So I didn't go into a whole lot of detail. I gave you the key idea, but once you do the majority, because you're doing the operation, you're actually wiping out all of the data because the bit line is affecting all of the cells, right? Mm-hmm. You're actually writing the data back into all of those cells. So what you really need to do is you do this in combination with row clone. First, copy the data to a location where you. So what we do in our implementation is have a special part of the DRAM array that's specialized to do this sort of computation, maybe 3 rows or maybe 10 rows. You can do triple row activation only in that part of the array, and you move the data or copy the data using row clone that we mentioned from the other part of the storage into that part of the array. This solves multiple problems.
And so even though you have to keep copying the data, it's still way cheaper than anything else.
Absolutely, yes.
Wow. And finally, the test you did with the FPGA, like, did you have to cool down the DRAM or do something, or just off the shelf?
No, off the shelf, basically. We don't need to change the temperature, although we did analyze the effect of temperature on the integrity of these operations, and we saw a small effect. But we don't need to do anything special. You can, as long as you're running DRAM under normal operating conditions, you can actually see all of these operations.
One of the online questions was that you've included the cost of physically moving the data from the memory to the computation with the memory energy costs. And we know electrical SerDeses have a certain cost per bit, some number of picojoules per bit. So how much of an improvement do you think we'll get if we have, for example, optical interconnect between the elements versus the current electrical SerDes?
Yeah, I mean, we have not examined optical as much, so I don't want to throw out numbers, but I believe you will get some improvement. Certainly part of the energy cost is due to the SerDes interconnect.
Is the actual physical movement.
And part of it is actually inside the DRAM movement. So these are, depends on the type of interconnect technology. These costs vary. But a lot of it is actually in the physical interconnect, no question about that. Those large interconnects that you drive off chip are a lot of the cost. That's why by doing near memory computation, without going into the analog computation, you actually get a lot of the benefits. Now, the energy benefit is a different, I mean, you still get a lot of energy due to the parallelism of the analog computation. But I cannot answer the question of optical. One of the downsides of optical is always a conversion, right?
Yes.
You have to convert between optical and electrical, unless you're completely operating on the optical domain, which is not easy to do today.
Yeah, that's a different topic, I guess.
Yeah, that's perhaps a different talk given by someone else.
Another online question is, do you have some prediction for when an application like this could be commercialized, and in what sort of area or field might it be commercialized?
I think probably the question is asking application like the analog computation, right? It's not completely analog, of course, because the sense amplifier does the digital to analog, analog to digital conversion. But yes, this triple row activation. I mean, I don't have a great sense, frankly. Frankly, the row clone operation, I'm surprised it's not commercialized yet.
Yes.
And I actually blame the mindset for that, because this is such a simple thing. I mean, we actually test any DRAM chip. You violate the timing parameters, you actually do this, get this row clone operation. It's so easy to do. But unfortunately, again, this is the mindset issue. The industry has evolved in such a way that memory is memory, no computation. Leave the task of computation to the processor.
Yes.
So that's the reason I don't think it is commercialized. Mbits type of a triple row activation, block bitwise AND and OR, that's harder because there are circuit level variation issues, which are less prominent with the row copy and row initialization. I don't know, but I believe it needs to be investigated. And if the industry changes its mindset a little bit, I believe it could be commercialized sooner rather than later.
And it could be that the near memory processing, it seems like companies are already working on prototype
That's
products
true, yeah.
and chips.
So I answered,
sooner.
yeah, I answered the question assuming the
Okay.
processing using memory, but near memory processing, I believe it's already commercialized actually. The UpMem company, which I didn't talk about because we didn't have time. I didn't expect to have time, by the way. But UpMem company already commercialized it. If people are interested, they can buy the chips. We actually did a lot of studies showing the upsides and downsides and what kind of computation could benefit.
Great.
I'd be happy to talk about that separately.
Okay, probably time for one last question locally. Anyone? Okay, great. Thanks again for a really fascinating talk.
Yeah.
Really appreciate it. Thanks so much.
Thank you.